Now that you know how to translate between all three types of motion graphs, position, velocity, and acceleration, this video is going to give you a bunch of examples of how to translate between all three types of graphs at once, from position, velocity, acceleration, and back down from acceleration to velocity to position. As you know from previous lectures, we can make multiple different graphs of the same motion using position, velocity, and acceleration graphs. For example, this person here, we can observe their motion and create a position time, velocity time, and acceleration time graph. So I can see that this person started off fast and then slowed down, and so I made this position time graph of what their position looks like over time. And we can also make a graph of their velocity over time. It starts large and goes down to 0, and we can also make a graph of their acceleration over time. Because they're slowing down, the acceleration is occurring in the opposite direction of their velocity, so it's negative. So all three of these graphs represent the exact same motion, just a different aspect of that motion: the position, the velocity, or the acceleration. So in this lecture specifically, I'm going to show you how, using information from one graph, you can understand what the other two graphs will look like. So as you know, the three graphs have this relationship between themselves. The velocity is the slope of a position graph, and the acceleration is the slope of a velocity graph. And the area under the curve of an acceleration graph is the change in velocity, and the area under the curve of a velocity graph is the change in position. We're going to be using these rules specifically to translate between a bunch of examples to show you how they work. And I found that a lot of students struggle with when slope is larger or smaller or positive or negative. So I've left this chart above my head to remind you of when slopes are which value. So a very steep upward slope is a more positive slope. A more shallow upward slope is a less positive slope. A perfectly flat line is a 0 slope, and then a slightly downward slope is a slightly negative slope, and a steeper downward slope is a slightly more negative slope. That's going to be really important in translating these graphs, so make sure you have that committed to memory. Okay, in this first part of the video, I'm only going to focus on translating between position and velocity graphs and back. So starting off with this steep straight line, I can see that this would be an example of a very positive constant velocity. So the velocity graph for this position graph would look like this. It's staying at the same velocity. It's a flat line because the slope of the position graph is staying constant. So because velocity is the slope of a position graph, a constant slope means a constant velocity. If I make this slightly less steep green line, I can see I have a slightly less large velocity because the slope is less large on the position time graph. This pink line that I just drew is perfectly flat, so that has a slope of 0 and it's constant, so that means the velocity is also constant and 0. And then this is a slightly negative slope and a more negative slope for a slightly and more negative velocity. So this graph you probably know how to translate as well. This is going to start off with a very positive velocity because it has a very positive slope. And then the second part will have a velocity of 0 because it's a flat line. And the third part will have a slightly negative velocity. It's closer to 0 than that first line though, because that last line is more shallow. And as a reminder, if you need help translating, you can always draw these vertical lines. These just show different time intervals. They don't really mean anything physical beyond that. So if you're having trouble seeing where the graph changes from one to the next, drawing those lines between the graph can definitely help. Here's an example where the position time graph has a constant negative slope, so therefore it has a constant and negative velocity as well. And here on the second part, it has a constant positive slope, so that means that the velocity is going to jump to being constant and positive rather than constant and negative. Here are a few more examples. I'm running through this quickly just to make sure that you get the idea of how to translate them before we move on. Okay, this is a new concept that we haven't seen before. This is a curved position time graph, and we want to understand how to convert it into a velocity time graph. So the issue with a curved graph is that the slope is constantly changing. That's the definition of a curved line. It's not straight, so it has different slopes at different points. So that means that the velocity is constantly changing also. So we need some way of understanding what the velocity is doing at different times. So my personal favorite trick for translating any of these graphs is to draw what are called tangent lines next to the graph that I'm translating if I'm trying to understand what the slope is doing. So a tangent line is a small, perfectly straight line that imitates what the slope of the graph is doing at that exact point where it's drawn. So if I were to draw tangent lines along this position time graph, they would look something like this. You can see that each one is imitating what the slope is doing at that exact point. So this is going to help us understand what the velocity is doing for every second that passes. So because the velocity is the slope of the position time graph, I can just look at these tangent lines to understand what the velocity is at different points in time. I can see, for example, that that first slope is 0, so that means that the velocity is also going to be 0 to start off. And then over time, the velocity is going from 0 to a little positive to more positive to very positive. That's what the slope is doing. So my velocity graph is going to do that as well. At a constant rate, it's going to go from 0 to a little positive to more positive to very positive. So that's what the velocity time graph would look like for this position time graph. It's going to be rare that you see a curved velocity time graph in this course. That comes up a little bit in the projectile motion unit, but besides that, it's relatively rare. And so for now, you can just assume that the velocity is increasing in a constant linear rate. So that's how you would translate that position time graph into a velocity time graph. We can try the same thing with this one now. Again, I'm not really going to think about this too much. I'm just going to draw those tangent lines next to the line of my graph and try to figure out what the slope is doing at each point. So I'm drawing those tangent lines. And looking at these tangent lines, I can see that that very first slope up top is very, very negative. It's going down very quickly. So that means that my velocity is going to start off very, very negative. And I can see that the final tangent line is 0, and all the tangent lines in between are becoming less and less negative. They're all negative, but they're getting closer and closer to 0 at the end. So that means that the velocity is going to start very negative and become less negative until it hits a velocity of 0 at the end. So that's what this velocity time graph would look like. This is another example. Again, I'm going to start by drawing those tangent lines. Okay, so here I can see that the velocity starts very positive. The position time graph has a very positive slope at the beginning. It then goes to 0 at the halfway point because it's a flat line at the halfway point. And then after, the velocity is going to be a little negative and then more negative and then more negative. So it's just going to keep going through 0 down into the negative. So that's what the velocity time graph would look like for this position time graph. We can now go backwards and translate back from a velocity graph to a position graph. So to start off, I'm going to imagine that we have this constant positive velocity here. I'm now going to draw those tangent lines on the position graph because I remember that the velocity tells me the slope of the position graph. So I know that because the velocity is constant and positive, the slope on the position time graph is also going to be constant and positive. Also remember that the velocity time graph tells you nothing about the starting position of the object. So I'm just going to imagine that it starts in the negative just so that I have enough room to go up. So I have these constant positive slopes that I'm adding. And so the position graph could look something like this when I draw it out. It could have also started from a different position. It could have started from the 0 point or up higher. It doesn't really matter. There are multiple correct answers here because the velocity time graph tells me nothing about where the position graph starts. I can see that this is another velocity time graph, but this time it's a lower velocity. So that means that the slopes are just going to be lower. They're going to be shallower like this. And again, I can start this from wherever I want. So I've decided that the position time graph looks like this in this case. Just a more shallow slope, still going up because the velocity is positive. This is at a velocity of 0, so that just means that the slope of the position time graph is going to be 0 the whole time. This velocity is negative, so as a result, the slope of the position graph is negative, and this is a very negative velocity, which means a very negative position time graph slope. Okay, so now we're getting into something new. We have a changing velocity, and we want to translate that into a position time graph. So I can look down and see what the velocity is doing at different times. So it's starting at a velocity of 0. So that means that the slope of the position time graph is also going to start at a slope of 0. So it's starting flat. And again, I can start the position time graph wherever I would like. The velocity graph tells me nothing about the starting position. So I'm going to start this a little high because I know we're going to be going down over time. So the slope starts at 0 and then progressively becomes more negative because the velocity is becoming more and more negative like this. So if I draw this out, this is what the position time graph would look like. It's a curve because the slope is constantly changing, because the velocity is constantly changing, and it's going from a slope of 0, where it's flat, to becoming more and more negative, going more and more in the downward direction. Okay, this graph is surprisingly complicated. This is a velocity that starts negative, goes to 0, and then becomes positive. So we can draw what the position time graph would look like. So this is going to start with a very negative slope because the velocity is very negative. And then I know the slopes are becoming less and less negative over time. They're going to a slope of 0 in the center. So I'm going to draw that out. They're becoming less and less negative over time. And then right here, it hits a slope of 0. And afterwards, the slopes are slowly beginning to get more and more positive. So the second part will look like this. So this is going to be this interesting curve here. It's going to curve down and then back up. It's very difficult to just eyeball these and guess what they will be. You need to pay very close attention to the slope and what the velocity is telling you about the slope. You can also use the area under the curve if you want, where each individual area under the curve tells you how much the object's position changes over time. So it basically also tells you the value of the slope. So here you can see that the areas under the curve can tell you the values of the slope. They're either very negative, less negative, 0, positive, or more positive like this. Okay, so now that we've translated from position to velocity and back from velocity to position, we can begin to translate from velocity graphs to acceleration graphs. Just a reminder, on a velocity time graph, slope is equal to acceleration. Like before, I'm just going to draw out these patterns super quick to show you how each individual velocity graph would be represented on an acceleration graph with a constantly changing velocity. Pretty straightforward. The acceleration is just the slope of the velocity graph. Again, the acceleration just shows you the value of the slope at that point. It's never really going to get more complicated than this for velocity time graphs because, again, we almost never deal with a curved velocity graph, and when we do, we'll use some special rules for it. I'm just going to run you through a few more examples really fast just to show you what a few more of these would look like, but I think you probably get the idea by now. We can also go backwards from an acceleration graph to a velocity graph. So here, this acceleration is constant and positive, so that means that the slope of the velocity graph will also be constant and positive. Here, the acceleration is 0, so that means that the slope of the velocity graph is also 0. Here, the acceleration is constant and negative, so that means that the velocity's slope is constant and negative. Here, it changes from negative to positive, so that means that the slope of the velocity graph will change from negative to positive. And the acceleration time graph tells you nothing about the starting velocity of the object, so you can start the velocities at any point you would like. You can also use the area under the curve of an acceleration graph to tell you what the change in velocity will be over that time. So now that you know these rules, I'm going to give you a few examples of translating between all three types of graphs, from position to velocity to acceleration and back. I'll start with this position graph. I can see that this has a constant positive slope, so I know that velocity is the slope of a position graph, so that means that the velocity is going to be constant and positive. And now translating from a velocity to an acceleration graph, I know that the slope of the velocity graph is the acceleration, and because the slope of that velocity graph is 0 over the whole time, that means that the acceleration is also going to be 0 for the whole time. So that is the exact same motion represented on all three types of graphs. So again, translating graphs means to express the same motion using a different graph. Just like translating a language means expressing the same idea in a different language. We can now translate this curved position time graph. It's curving up, so I can see it starts with a slope of 0 and the slope gets bigger and bigger and bigger over time. And so that means the velocity is going to start at 0 and get more and more positive over time. And now to translate from velocity to acceleration, I can look at the slope of the velocity graph and see this is constant and positive. So that means that the acceleration is also going to be constant and positive. So the acceleration time graph will look like this. Here's another example. This time we're given a velocity graph and asked to translate to a position graph and an acceleration graph. So I'll start with position. So I can see that the velocity is starting very positive and over time becoming less positive until it hits 0. And then it's becoming more and more negative. So that's what my position time graph will look like. And my acceleration time graph shows me the slope of the velocity time graph, and that slope is constant and negative, so the acceleration is also going to be constant and negative. Here's one last example of going from an acceleration graph to the other two. So I can see I have a positive acceleration and then a negative acceleration. So that means that my velocity is going to start with a constant and positive slope, and in the second half it will have a constant and negative slope like this. And again, I decide where the starting velocity is. Here I decided it's around 0. And now going from velocity to position, I can see here that the position graph is going to start with a slope of 0 because the velocity is starting at 0. I kind of arbitrarily decided that. And then it's becoming more positive over time until it's very positive at that central point. And then after that, it's going to become less positive until it hits a velocity of 0 again. So this slope is going to become less positive, and it's still positive. It's still going up. It's just going up at a less steep slope than it was before. So it's going to keep going up at a slower and slower rate until it hits 0 again. So this is what the position time graph of that object represented in those other two graphs would look like. Okay, that was everything. That is how you translate between all three types of physics graphs.